Hey, Algebra 2. Today we're going to look at problem set 22, and we have two topics in this lesson. First is what's called uniform motion, and we're going to look at our first distance problem, and we're going to look at what's called equal distances. That should be a big clue in what our equations are going to look like. And then a second topic is a little bit more with similar triangles. We've been dealing with that for several lessons here. We're just going to touch on it one more time just to make sure we're getting the hang of it. Okay, so the first problem here is we're going to talk about these distance problems. Your book refers to them as uniform motion. I will probably call them distance problems. Okay? Now, the thing you need to remember about distance, this is something you should have talked about in physical science or maybe in a previous math class. And this idea of distance is equal to rate times time. Okay? That should be something familiar to you. Distance is rate times time. Now we're going to set up an equation, and in most of these problems we're going to be dealing with two distances. Sometimes the distances are equal, sometimes they will add together to equal some total distance, or we'll have a third example here coming up in a few lessons. But to start off, we're going to talk about equal distances. Now what I suggest on these problems and the way I work out the examples every time is you should start with a little picture, trying to describe or demonstrate what's happening in the problem, and that will help you set up your equation. Okay? With these two distances, most of the time you're going to set them up, and this is where those subscripted variables come in handy, because we want to still be talking about two different rates, but we want to make them different. So we'll call it rate 1 and rate 2, or rate for one person and rate for another person. So we can still call them R, but we label them a little bit different with the subscripts. Okay, so let's look at this first example, and I'll show you how I would set them up, and then we'll see what we can do. Okay, on Tuesday, the express train made the trip in 12 hours. On Wednesday, the freight train made the same trip in 16 hours. Find the rate of each train if the rate of the freight train was 15 kilometers per hour less than the rate of the express train. Okay, so we got to think about what's happening here in the problem. It starts off and says the express train made a trip. So I'm going to start with a little picture. Here is the distance for the express train. So I'm going to call that distance E. Okay? Then on Wednesday, the freight train made the same trip. Okay? Key word, same trip. So here goes the freight train. Makes the same trip. So I'll call this distance for the freight. Okay, so right here, I see my picture. I have the distance for the express train and the distance for the freight train. Right off the bat, I should recognize that these two distances are equal. So the distance for the express is equal to the distance for the freight. Okay, now before we go any further, I would change this distance into rate times time. The distance for the express train is the rate of the express train times the time of the express train. And that's where I'm going to use the little subscripts, R sub E, T sub E, rate express, time express, equals the distance for the freight train is the rate for the freight train times time for the freight train. Okay, so here's my main equation. Something like this should look familiar because we've done some problems in some previous lessons with these subscripted variables, and the book used the R's and the T's just like this. So this should be something we're familiar with. Okay, now we look at the problem and we pull out as much information as we can on what we know about any of these rates and times. Okay, so we start off again. On Tuesday, the express train made the trip in 12 hours. Okay, that 12 hours, that is the time for the express train. So I know the time for the express is 12 hours. All right, on Wednesday, the freight train made the same trip in 16 hours. So the time for the freight train is 16 hours. All right, so I know both times, so I will plug those into my problem in just a second. But let's see if we know anything about rates. It says to find the rate of each train if the rate of the freight train was 15 kilometers per hour less than the rate of the express. So we can translate this just like it's written. The rate of the freight train is 15 kilometers per hour less than the rate of the express. So the rate of the freight train is equal to the rate of the express train minus 15. Okay, now there's other ways that we could set up an equation like that. but let's just go with this one for now. So what I have here is I know 3 out of the 4 variables, similar to some subscripted variable problems that we did in our book. I'm going to take these 3 things, plug it into my main equation. The one variable I don't know is RE, so RE has to stay in the problem. I'm going to plug in TE, which is 12. RF is that group. Make sure you plug it in using parentheses. So that's RE minus 15. TF is 16. All right, so now I can solve for RE. This is 12RE equals, we'll distribute this 16 into both, and that is 16RE minus, I did not work this out ahead of time, so 15 times 16, sorry, I'm doing some math here, 240. Hopefully I did that right. Okay, now we can finish solving here. Subtract 16RE. So that's negative 4RE equals negative 240. And then we divide both sides by negative 4. Luckily, those negatives will cancel, and we get the rate of the express train is 60. That's 60 kilometers per hour. Okay, now the problem says find the rate of each train. I found the rate of the express train is 60. Now I can go in here, plug in a 60, and I can find the rate of the freight train. 60 minus 15 is 45 kilometers per hour. Okay, so hardest part of the problem is getting this main equation set up and pulling out this information that we're given in the problem. Once you get that main equation and you pull out the information, it's old stuff. It's stuff that we've already done. Okay? Let's try another example. Alonzo ran off toward Milano at 9 kilometers per hour at 8 a.m. At 10 a.m., Wilhelm began the chase from the same starting point. If he caught Alonzo at 12 p.m., how fast did he run? All right, so let's start with our picture. We have Alonzo. He took off running towards Milano. So here's our distance for Alonzo. Okay, a little while later, Wilhelm began to chase after Alonzo from the same starting point, and he eventually caught up with Alonzo. So here's distance for Wilhelm. He eventually caught up. Started in the same place and eventually caught up. So there's my picture. These two distances should be equal. So we start off with our equation. Distance Alonzo equals distance Wilhelm. Now again, distance is rate times time. So we turn these distances into rate times time. Rate Alonzo times time Alonzo equals rate Wilhelm times time Wilhelm. All right, now we look at what we know. Alonzo ran off towards Milano at 9 kilometers per hour. That is a rate for Alonzo is 9 kilometers per hour. At 10 a.m., Wilhelm began to chase after him from the same starting point. We don't know anything about Wilhelm's rate. Okay, so that one we don't know. Let's look at time. Okay, we need to look at what time Alonzo started. Alonzo started running at 8 a.m. We need to look at what time he got caught. He caught Alonzo at 12 p.m. So Alonzo ran from 8 a.m. to 12 p.m. How many hours is that? Well, from 8 a.m. to 12 p.m. is 4 hours. So the time for Alonzo is 4. All right, now we look at Wilhelm. I don't know how fast Wilhelm was traveling, but I do know that he started at 10 a.m. and he caught Alonzo at 12 p.m. So from 10 a.m. to 12 p.m., the time for Wilhelm is 2 hours. So the one thing we don't know is the rate for Wilhelm. That's what we'll solve for. So I know 3 out of the 4 variables. I plug them in. RA is 9. TA is 4. RW we don't know. That stays. Times TW, 2. All right, we're ready to solve. 9 times 4 is 36. RW times 2 is 2RW. Now we finish by solving for RW, divide both sides by 2, and we get RW is 18. So there's our answer. If he caught Alonzo at 12 p.m., how fast did he run? Well, he ran at 18 kilometers per hour. Now, one thing that was not done in these problems is every now and then you will be asked a question like this, how fast did he run? But then they'll also follow up with the question, how far did he run? What was the distance that they traveled? So if I want to know distance, say distance for Alonzo, I need to know the rate Alonzo times time Alonzo. So if it ever asks the distance, I go back now and I pair up what I have. The rate for Alonzo was 9, time for Alonzo was 4, so his distance was 36 kilometers. Now we can check Wilhelm. Distance for Wilhelm is rate Wilhelm times time Wilhelm. His rate we found to be 18. His time we figured out to be 2. We multiply that together. Distance Wilhelm is 36. Now this is a good way to check yourself because we said at the very beginning that these distances are equal. So we checked it out and they are both equal. All right, every now and then again you'll be asked what was the distance traveled. So you'll have to pair up the rates and the times. Okay, now second topic in this lesson again is similar triangles and using proportions. This is review. Same stuff we've done. In a picture like this, I'm given two angles are equal, the ones with the single marks. You also need to recognize that these angles in the middle will also be equal because they are vertical angles. And now on all these problems, it's best to pull the two triangles apart, redraw them positioned the same way. So this is 6, that's 9, that's 7. I'm going to spin the other little triangle around, position them the same way. And be careful when you put the marks in there. The side between the 1 mark and the 2 mark is Y. So Y goes there. The side off of the 1 mark is 5, so that's here. And that leaves X over here. All right, now again, you want to pair them up. Pair up the matching sides. Find the two sides that you know both lengths. That's your 6 and your 5. That is your starting point. That is your ratio. 6 over 5 equals, and then pair up the other two sides in the same order. 6 is on top, so I use the 9 on top over its matching side, Y. And then 6 over 5 equals 7 over X. And now we simply cross multiply and divide to solve for Y. So we get 6Y equals 45. Divide both sides by 6. 6 does not go in there evenly, but we can reduce. We can divide them both by 3 and have 15 over 2. So that's Y. Down here for X, we cross multiply. We get 6X equals 35. Divide both sides by 6. And this does not reduce. We can leave it as 35 over 6. Okay, again, this is old stuff we've done for a couple of lessons now. So we just want to touch on it again and review, make sure we're okay setting up these proportions. Again, pull the two triangles apart, spin them around, position them the best you can the same, and then set up your proportions. Okay, now what I want you to do here, you should see on your page that I have a couple of extra problems. What I want you to do now is to pause this video, work out those examples, and once you have them finished, hit play, excuse me, hit play, and you will see on the screen that I have worked out the same problems, and you can check your answers to make sure you get the same thing that I did. If you do not get my answers, then you know you need to go back and check your work, see if you can find your mistake, and if you're having any trouble, those are the problems that you need to ask me about. Okay, so right now, pause the video and work out those examples. Okay, here's the two examples. Hopefully you can follow my work here. I tried to show every little step and see if you have any questions on these problems, okay? Again, this is our first type of distance problem where the distances are equal. We will do a couple other types of distance problems in a few lessons, okay? And again, some more review with the similar triangles. All right, this is lesson 22.